Hello and welcome to session 297 in the AISafety.com reading group. Tonight we'll be discussing Against the Singularity Hypothesis by David Thorstad. David Thorstad is a senior research affiliate at the Global Priorities Institute and assistant professor of philosophy at Vanderbilt University. This is an article that was published around a month ago, but it was actually circulating in draft forms at least back to November 2022. And as always, the speech balloons are my personal opinions, and the faded ones are things I don't consider important, and the gold ones are things that I'd like to discuss. You can see my screen now. By saying thank you to David for examining the arguments for AI safety. I think this is one of the most important things you can do, because if this really is a problem, then figuring out if it is a problem is extremely important. And I also must say that I'm very impressed with the quality of the arguments. Recalcitrance is a word that I've never heard anyone else pronounce, so I might pronounce it very wrong. So as far as I know, David is the first person to have a critique of Bostrom's work that is specific enough to actually use that word. And as always, sometimes when I summarize David's words and make the arguments, sometimes it becomes a bit compressed, and I apologize for any errors in advance, or if there's something from an earlier draft that I've included. So one of the obvious things we can conclude is that if this has been circulating since ChatGPT was released, it seems in an important sense that David was right, that OpenAI is using ChatGPT to improve ChatGPT. So we are by definition in a textbook takeoff, and since there's no singularity here, it seems like the first half of the takeoff is slow. So that's of course no guarantee that the rest will be slow, but there is, I think it's important to acknowledge that in a strong sense, David was right. Tonight, there are two broad topics. The first is the singularity thesis, and the second is AI safety. These two are importantly distinct, but also have a substantial overlap. And while I do have opinions about the things to the side, I hope to focus on the intersection between these subjects, which is quite large. Let's start out with a definition of the singularity thesis, which David defines following many others. It's a reasonable standard definition, that there's a quantity called intelligence, which is well defined in a number of ways that can be argued against, but that David, for the sake of argument, grants is meaningful. And this quantity is increasing, either strongly exponentially or hyperbolic. I think in general, I think only of singularities as hyperbolic. I recognize that in practice a very strong exponential function is almost as powerful, but to my mind it feels easier to bin them as separate things. And this quantity of intelligence needs to increase very rapidly for many orders of magnitude. And David writes that it needs to be for a long period. And I think the period isn't that important. It's the difference in intelligence that matters. The period could be very, very unsustained. Even if it's just a second, that's not really what matters. The key part also for the singularity thesis is that the growth covers the area from a roughly human level until a level where AI are powerful enough to take over or upload us if that's what we want or they want. So the discontinuity inherent in this singularity thesis is in power, and it's not a discontinuity in some of the graphs that people sometimes erroneously, I believe, show. People also sometimes define singularity by this event horizon thing from physics, where you can't see anything behind it, the opacity, and I also think this is a worse definition than the one David Thorstad uses. So I'm very happy with this. Now, what is the relevant characteristics of singularity from an AI safety point of view? This is Bostrom's graph of the takeoff, scenario. And to my mind, the two important criteria for singularity is that there is some kind of hyperbolic growth that continues to a level that is above, substantially above civilization. So the y-axis here, I think like an order of magnitude. That means that in practice, if the AI wants to take over, they can do that. And also the hyperbolic growth must be such to that there will be a time, let's say within 24 hours, where the capability doubles. So this means that effective response is in practice impossible. So both of these are defined through what is important to AI safety, and that isn't actually what the original proponents of singularity, the singularity thesis, argued for. So even though these don't match perfectly to the singularity thesis that David writes about, I hope they will be close enough to some extent. I also have a few comments about the parts of the singularity thesis paper that doesn't relate to AI safety. I'll try to go over this quickly because I'm somewhat out of my area and most of this are reasonably minor points. The first is that there's a lot of things in the paper that I'm just going to skip. Like long-termism, to my mind, is basically short-termism because I have short timelines, and Chalmers' observational argument, I believe we've discussed here previously and concluded that it's basically fully superseded by Bostrom's 2014 superintelligence. I have a funny comment to a model referenced by David that postulated infinite population by 2026. I think this is a joke paper in some sense, and there's a saying, one man's modus tollens is another man's modus ponens, and I think this is basically what happens here. That the person who made this model made this as modus tollens to show that there was something wrong with the premises, and Kurzweil basically took it to the logical conclusion and said, hey, this means that we will have a singularity, not precisely 2026, but pretty close. I do also have a number of comments on the treatment of Bostrom's superintelligence, because in general I think he deserves a lot of credit. He is, I'm very happy about his treatment. And I think some of the arguments presented by David Thorstad, in fact, all five reasons to question the growth are mentioned in Bostrom's book, and Bostrom believes that they are powerful enough for this. There is the characterization of how likely Bostrom considers a fast or moderate takeoff, whether it's likely or highly likely. And in particular, Bostrom has this important qualifier to the part about the speed of the takeoff, that if it's done basically using compute, we will have a slow takeoff. And I think this is roughly what has happened, in fact. The way we have built these large language models have been in a way that cannot really be cheaply scaled. And that is, in fact, why we're having a slow takeoff right now. There are also a number of other arguments from the book Superintelligence that aren't really mentioned in much details. I won't go through them here because obviously they are not mentioned in the paper, but that's one thing I want to add. There's one thing in particular that I think is worth to highlight in Bostrom's treatment of a singularity. And this is one where David Thorstad claims that Bostrom is factually incorrect. And here is like the rough area, and in Bostrom's superintelligence, and it says here, this leads to the system doubling in capacity every 18 months with a parenthesis. This would be roughly in line with the historical improvement rates from Moore's law combined with software advances. So this David Thorstad raised this as Bostrom saying that the AIs have been improving in intelligence every 18 months, and that means that in practice since the last 40 years we've seen intelligence increase by a factor of 33 million, and that seems like very wrong. And I've tried to read this closely, and I actually agree that the sentence that Bostrom is saying can be interpreted in the way that David is doing. Like, you can both say that this kind of doubling in 18 months is the kind of doubling that Moore's law have, or you can also say that history shows that the intelligence of AIs doubles every 18 months. And that is in fact a very ahistoric and very poor description of the growth in AI intelligence, especially before 2014. So I think when I read Bostrom's, I used the first way of passing the sentence, but I think I would accept that this part of Bostrom's book, Superintelligence, isn't that clear and that well written. So I will try later in this discussion to explain basically the same thing. The second part of the Venn diagram that I showed earlier are things that are related to AI safety, but not the singularity. And this is, of course, a place where I consider myself a bit more informed, in fact, substantially more informed. Here, David Thorstad summarizes the Bostrom-Yudkowsky argument from AI X-Risk to be based on the orthogonality thesis, instrumental convergence, and the intelligence explosion thesis. And I'm not entirely sure I agree with this characterization. Orthogonality is a very, very tiny detail. It's like one paragraph countering the argument that if the AI becomes smart, it will automatically be nice. And basically no one makes that argument any longer. Instrumental convergence, I absolutely agree that this is one of the load-bearing theses. The intelligence explosion is something that Yudkowsky and Bostrom puts a substantial probability on happening, but it's not really that central in the thing that if we get more time, because we don't have a fast takeoff, we need to use that time productively. And the key issue is that we can't use this time productively because alignment and AI control is just really, really hard. And that, I believe, is the central part of the book Superintelligence. It's like literally half the book Superintelligence. So I believe this is one of the key premises that the Bostrom argument for AI X-Risk is based on. So basically, the idea is that even if no intelligence explosion happens, the argument for doom is still holds. And the counter-argument presented by David is that if we don't have a singularity, we get more time for safety works, we don't get very extreme capabilities compared to the others, and we're more likely to waste our time in AI safety work. And I think this is an important question. I think all of this is true. I think the quantities are not that much, but actually I would prefer not to talk about this. I would much prefer to talk about like the intersection between AI safety and the Singularity Hypothesis. So let's start by talking about like simple explanation and parsimony. What is like philosophical parsimony, of course. So this is my example of trying to explain the singularity thesis in a way that is not robust to adversarial interpretation. I'm trying to explain like how the model in my brain works, and I expect that just about all the statements I made can be attacked because it's not that formal. So here is a graph of intelligence on the y-axis or capability, and then time on the x-axis, the t-axis. And as you can see, the system capability grows. If we are now in like the 6th month of 2024, then on New Year's Eve 2025, we get a singularity. And that is the graph y equals minus the natural logarithm of 2025 minus t. And this, of course, has a vertical asymptote where c equals t, because then it's the logarithm of 0, and that is infinite. So this is a surprising claim in need of justification. And I think that is a very reasonable thing to say, right? You can point to this up here and say, what is this? This isn't the kind of thing that you see very often in your day-to-day life, to say the least. And the graph itself, it's like I find it looks like a hockey stick, right? This seems like a kind of non-parsimonious explanation. And What I will try to argue now is that this formulation y equals minus the natural logarithm of c minus t is in fact a really simple natural construction that should be considered the most parsimonious explanation for the data that we are seeing. So, to do that, I need to establish a couple of things. First is, of course, we have William of Ockham saying that when we have different explanations of the observed data, we should prefer the simplest one, or I think he did in fact say something quite different with not like multiplying the terms or something like that. I can't remember, but it's commonly referred to as something like this, the principle of Occam's razor. So let's say we have a simple observation. My hair becomes 1 millimeter longer every day. One hypothesis is like there is a stepwise function, like every time it's midnight my hair grows 1 millimeter, or we could have some kind of continuous hypothesis where this like dy dx, you may be familiar from calculus, that the difference in length compared to the difference of days is 1, and that's the classic linear growth model of my hair. And I think in an important sense we should say that hypothesis number 2 is simpler than this stepwise function. So one way of writing this here is proportionality dy, which is my hair length, dt is 1. So this is the standard linear function. We are just changing the units. So normally linear functions would be something that has a constant a, but we're just changing the units, so it's basically just equal t here. So this is a very simple model, and I think most people would agree that, yeah, this is a simple natural concept, and if you're trying to model something and it seems like it is like has this kind of proportionality, then yeah, probably it's a linear function. That should be the default explanation. Now let's make another observation. We note that the number of transistors on a chip is doubling every 1.5 years. We could again make several different hypotheses about this. The first is, yeah, we are having this standard improvement, this exponential increase that Moore's law says, or we could have the same thing but with some kind of diminishing return factor. And these are both explanations, and in an important sense, I think the first one is simpler. For something that's very easy to measure, like the number of transistors on a die, then getting the observations that could justify the second is probably really easy. But the first thing we should consider is probably a model of the kind of number 1. So this is what I now call an improvement, which has this this gradient, which if you try to figure out which like calculate which functions satisfy this, you will find these are the exponential functions, and these two are of course connected in a strong way. For an economist, it would be the most natural thing to relate these two, because you have compound interest, where you the amount of money that you have is compounding exponentially. As a computer scientist, I feel the most natural way of thinking this is through recursion, that we're recursifying, that we are taking the output and putting it in as input, which is basically what you do if you have like a bank account where you get some interest and then you put that interest back in the account and then you compound interest. Some people also call this process folding in on itself. And I think all of these three concepts are reasonably natural. And if you have some kind of process, then looking at these components seem like reasonably simple things. It's not something that I can really strongly argue. This is showing my intuition that these things are natural in some sense. Now let's talk about recursive improvement. So we had the idea of proportionality, that you could recursify to get an improvement. So what happens if you have an improvement and you recursify that one more time? Well, you get recursive improvement. This is the idea behind recursive self-improvement. How natural is that? It's a good question. Like I feel that it's a reasonable natural concept, and that some processes you could imagine, yeah, they should be modeled as a recursive improvement. Another way to look at this is like you have a recursive proportional process. I don't know if that makes it clearer. Perhaps if you see the three the three gradients next to each other, you can see this proportionality improvement and recursive improvement. So this is basically one of the key points I want to make. That if you're talking about recursive improvement, then the most simple parsimonious way to model that is with a dy dt that is the exponential function in y. That is the most parsimonious model. That doesn't mean it's the correct one, just that it's a good starting point. Now what does that imply? Well, if you start with dy dt equal e to the yth, then this is a separable differential equation, so you're allowed to do this. If you only have high school calculus, then you're taught that you're not allowed to do this, but you are actually. And you can integrate both of the sides. We're doing that here. And then you can, this left side is 1 divided by e to the yth, so that's the same as e to the minus yth. And the right side here is basically t plus a constant of integration. So this means this here and this is the same here, so we combine them. And the integral, the antiderivative of e to the minus y, that's just, we take the minus out here. So we get this equation here. We can multiply both sides by -1, take the natural logarithm of both sides, and with a very quick change in the constant c, we have basically this. So that means that if you have something that satisfies this, it will always be on the form y equals -ln of c minus t. So that's basically the idea, that if you have something that grows in this exponential way, it becomes, it gets this asymptote basically. So how robust is that in some sense? Like how many complications do you need to add to something before it stops implying a singularity? Again, this was the conclusion from the previous slide. And now we are adding some constant like 0.5 or something like that. And I've tried to write some of the conclusions. So if you just multiply this by 0.5, the way this includes the graph is we multiply time by like 0.5 again. So that's basically that if you add a constant factor, it corresponds to slowing down time. So if you add a factor 50%, then you get twice as much time before the singularity. If you add a constant to the exponent in the exponential, then you get even more time, but you don't avoid a singularity. If you have the growth divided by t, then you get even more time, but you still don't avoid a singularity. What if you have a counter exponential? So you have one exponential, the first one with a factor a, and then you add another that has where you divide it by b. So it's a minus b. Well, then you get something that looks like this. So this is a constant, and of course, if that constant is very close to 1, then you get a singularity. If it's very close to 0, you get something that grows very slowly. If it's negative, then it basically fizzles out. So if you have one exponential growing factor and an exponential damping factor, I think in general you will get something that either very quickly diverges towards infinity or fizzles out. You can also have other examples. You can divide it by y. That doesn't have a vertical asymptote and it's a transcendental function, which is really difficult to work with. You can have logistics functions which are way nicer, and they of course like this kind of sigmoid S-curves strongly stops. So if you can find something like that, then you will not have a hyperbolic growth. Basically, how robust is the idea that recursive self-improvement leads to hyperbolic growth? I think like moderately robust, but I don't have a really strong conclusion, and I don't have a strong conclusion of, on any of this. Okay, so that was the idea why we would expect a singularity as the most parsimonious explanation. But let's go to some of the observations. One of the observations that we have obviously seen are diminishing returns. And the idea that we can have exponential growth is in fact not obvious. Sometimes we can have that for a period and then it fizzles out. In many limited cases, I believe that exponential growth, like if you ask what will be the growth of the economy of the United States over the next years, most people will answer like in percentages. And I think for many kinds of processes, this is a weak assumption, probably even the weakest. It's to a large extent, this depends on like what are your timelines, because if you believe that AI safety won't be relevant for another 100 years, then the claim that Moore's law will continue for another 100 years looks like a really strong assumption. If you believe we have a couple of years, then something like Moore's law seems much more reasonable. There is a quote here. Research productivity, understood as the amount of research input needed to produce a fixed output, falls with each subsequent discovery. And I think here it's important to distinguish between a fixed output that is like linear proportionality or an improvement that's for the exponential. Like modern researchers can very easily do extremely impressive things that doesn't really improve the state of the art that much. Like in a fixed absolute sense, like doing a multiplication in the medieval age meant creating gears, and that took like years. And right now, even a really poor researcher can do many doing a tiny improvement on something will probably, in some absolute sense, be much greater. That's in general, however. And sometimes researchers can't really. They get stuck. They get into some kind of dead end where they can't actually do something. So my overall conclusion on this is that this is pretty noisy and contingent, and like very low productivity is probably reasonably rare. Sometimes researchers certainly can do like a lot of improvements. How about Moore's law in particular? David makes the claim that Moore's law is dead. I agree that if you use it for just counting the transistors on the chips, we are below the expectations. But if you look at something like AI hardware, then AI hardware is growing, as far as I can tell, in floating point operations per dollar, faster than predicted by Moore's law, and that's been going on for a long time. We've of course seen improvements in transistors per chips, and that wasn't something that caused an intelligence explosion. And the precise reason for this is that this is an improvement process and not a recursive improvement process. The classic example of a recursive improvement process is if the engineers are emulations and they are running everything on the chips that they are building themselves. In that case, it would be a recursive improvement process, and if there are no defeaters or counter exponentials, then yes, that would cause a singularity. Bostrom has an illustrative example in this box 4, which shows a singularity after 18 months. And as David points out, this didn't in fact precisely happen, because while we did see a huge speed off, 33 million times speed off, we also saw that we had to put in 18 times more effort. So that comes out to, according to my calculation, every 18 months they need to like build 39% more factories, which seems hard but doable, I guess. So of course they were able to do that in practice, just build more factories and hire more people. But even if they had not been able to put in more effort, then 39% more effort isn't enough to counter a singularity. Because if we imagine that this 1 to 18, the fact that it becomes 18 times harder was distributed evenly over the 25 doublings that are inherent in 33 million times speed up, then that just comes down to slowing time down by this factor 18 divided by 25, and that means that Bostrom's model that predicts a singularity in 18 months turns into a model that predicts a singularity after 25 months. So we get more time because of this kind of diminishing return, but not enough to stop the singularity. Here I should add that the math easily can become confused because the Bostrom has a model where we get a singularity within 18 months, and David is saying that it's missing a factor 18, and the way these 18s go against each other means that there's a probability that I made a math mistake at this point. But I think I did it right. The next argument David Thorstad makes is about bottlenecks and physical constraints. So if we have some bottleneck to our improvement process, that could slow the growth. And there are, in fact, some bottlenecks that can slow it, but I believe that they are not very applicable to the models that we're seeing right now. Because if we expect that AI progress, like in large language models, are driven by improvements in hardware, algorithms, and budgets, then if one of them is bottlenecked for some reasons, but the other two continue to grow, then we'll get 1/3 of the progress, and that doesn't stop hyperbolic growth if we just cut the growth in thirds. We don't really know about how much hardware can be improved, how much algorithm, how large can the budgets get. So we should expect bottlenecks. It's an epistemic question whether if the fact that we are uncertain about that means that we should expect that they can't be improved that much. It could also be because that we are uncertain about this, that it will actually be possible to increase them more than we think. And if it turns out that there is a huge bottleneck somewhere, then there's going to be a lot of work to go into fixing that. Another issue is there are some physical laws that says like you can't put the chips closer together than this. Information can't travel faster than the speed of light. There's a Landauer limits and all these. And I agree, they are limits, but they are also really, really high above what we are currently doing right now. There's also the claim that if we have, we do have some theoretical ideas about what is the best achievable performance we can get. And like, this means that there is some limit to how much we can make them faster, and that is true. Like there is an optimal Bayesian reasoner that we can say some things about how good it would be at reasoning, and it seems like that is very, very far above the levels that we're currently at. Okay, the next argument is how much does intelligence grow from improvements, which is something like faster chips. And more transistors. So this is a different claim. Normally when we talk about the intelligence explosion thesis or the singularity thesis, we're talking about like intelligence over time. And now we are talking about over the number of transistors. And this is a very different claim in the sense that it is possible that intelligence grows extremely slowly in the number of transistors, but very fast in time if the transistor count is growing sufficiently fast. So we, in some sense, have dueling exponentials here. So the first claim that David makes is that it seems intelligence grows sublinearly in underlying quantities such as processing speed. And I think this is true, but it's also very weak. Like sublinear is much too weak to counter a singularity. But of course, if you run GPT-3 twice as fast, then it's not able to like do twice as much in some qualitative sense. It certainly does not have twice the IQ. And the way David models this is that exponential increases in underlying computer capacities lead at best to linear improvements in intelligence-related tasks. I think this is sometimes true and also sometimes false, depending on what the task is. An obvious counterexample would be social persuasion, which is something that is really important from a capability point of view. And if you run the algorithm twice, then it can interact with twice as many people and to some extent get twice as good results, right? So sometimes we do in fact get precisely linear outcomes from it. In practice, my model is that things are way more noisy. There are a number of things you can't do if you are like slow or at some slower than some level that you can do if you are not. And there are some a lot of interesting capabilities that are very discontinuous. So I think in general this reality is way more noisy than that. What does this imply for hyperbolic growth? David says we shouldn't ask that question, and I think when I read this question first, it wasn't actually clear to me that the hyperbolic growth was in transistors and not in time. And of course, as I showed before, This depends on how fast the exponentials are, because if we get a one recursive improvement that has like a high factor and this is a low dampening factor, then we might still get an intelligence explosion. The final part I want to talk about is quality superintelligence. It seems there's a qualitative sense in which I can't reason in the way Albert Einstein can do, and it's possible that there is an AI that can reason qualitatively in a way that Albert Einstein can't. This is what David Thorstad calls restating the core hope, which I think this is not Bostrom's hope, it's his fear. And this is the argument, the area where David Thorstad finds Bostrom's argument like insufficient. The first way that he argues this could be done is like we can go from processing something in a narrow sense to something general. Bostrom kind of alludes to the difference between narrow intelligence and general intelligence by making a comparison with animals. I think in practice we've seen this happening sometimes, where we have large language models that can't do modular arithmetic, and then suddenly they are smart enough to grok it, and then we get this kind of very dramatic capability increase. The second is, of course, that the programmers could get some kind of insight in, like, what is intelligence. And Bostrom doesn't spend a lot of time on this. In particular, there he says everything could happen in like one key insight, and he basically spends one sentence on this. So I think to a large extent, I agree with David Thorstad that Bostrom doesn't argue sufficiently for this. So let's figure out how plausible is it that intelligence can be improved in this kind of qualitative sense. So again, this is something we can't know. Like if someone claims that they really know it, then I would disregard their opinion basically. I.J. Good famously said that this is unquestionably true. And I think that is way overconfident. This is in fact a really difficult question. And I think this allusion to quality is the central parameters in Bostrom's book, but it's just very difficult to get a grip on. Richard Sutton has given the example of the bitter lesson that if you try to build AI by leveraging the ideas about intelligence in a qualitative sense, then that basically doesn't work, or it's at least a lot less effective than doing it in some way that better leverages computers, basically searching for it. And I think this is an important point, that a lot of people have had this kind of intuition that it must be possible to build a general AI through some process that revolves around understanding how intelligence works, because they can introspect to that. And they have spent a lot of time trying to do that, and they have basically failed. So I believe we're currently really confused about intelligence, and the way we are doing AGI right now is just brute search, basically, because we really don't understand it. That's not really a strong guarantee that we won't actually get this kind of understanding. Like, it seems the obvious thing that we grasp for some concept and we don't understand it, we get a key insight, and then we are no longer confused. So, in my conclusion, will there in fact be a singularity? What is my probability of a singularity? I think my key crux is something like how understandable, compact, beautiful, implementable, improvable is intelligence. And if I come to believe that intelligence is something that has this kind of beautiful centralized theory that you can implement in a computer and perhaps improve on, then I believe a singularity is more likely. And if intelligence is some concept that is too difficult for humans to really understand, like there's no guarantee that humans should be able to understand this in the same way that like a dog will never understand quantum mechanics, right? And to the extent that I think this is not a thing that can happen, then I also think a singularity is very unlikely. One of the ways, kind of strange ways that I get a lot of my intuition from this is from reading Probability Theory, The Logic of Science by E.T. James, where in particular the first third of that book tries to describe intelligence using a mathematical formalism that is really, really beautiful. And he doesn't, of course, get to AGI. That's really obvious. But you have this feeling that he describes intelligence in a way that is extremely amenable to implementation. And if he'd been able to continue to AGI in such a beautiful way, then we would have been able to implement it on a computer and build a super intelligence that would easily do a singularity. That is, however, a thing that a lot of people have tried. And I think right now, large language models are all the rage, so people aren't really trying to build a beautiful mathematical formalism for intelligence. And that means that my probability of an AI safety relevant singularity, something that crosses the capability of society and does it very fast, is quite low. I think maybe 5% or something like that. I also get the intuition that there is, in fact, some core to intelligence that is beautiful, that is improvable. And I think I could see a 250 IQ AI just straight up figuring out intelligence and implementing a very simple, beautiful AGI that is strongly super intelligence. I think that is the thing that could happen, but I think this is something that is likely to happen after AI has killed us all. So that is all for today. Thank you and see you next time.
In order to get a certain level of performance increase, you fundamentally need logarithmic increases in those computational inputs. But like,
okay, David, do you have an answer to Lau Mein? I'm not entirely sure I got the question, Lau Mein. David, perhaps.
Yeah, maybe we could do one point at a time. Was there one you wanted me to start with?
The logarithmic. The sigmoid function thing that, in some sense, a true singularity. Everyone agrees in some sense that a true singularity is impossible. Which I'm not sure what your opinion on that is. Do you think?
Yeah. So that's what's going on with like the person saying, we'll have infinite population in 2026. Is like nobody who writes down a hyperbola actually believes a hyperbola, in the sense that we're talking about something that's not going to go infinite. And so it gets like a little hard to say what we mean by a singularity, because what we mean is, we're going to follow the hyperbola for a while and then we're going to tail off. And so, I think that's a way of agreeing that like all the singularity people, the graph we're looking at right now, like all of them agree, it's a graph like that. It's just a question of how high and how fast.
Okay. Yeah, I think we agree on that. And you do agree with the logarithmic increases in intelligence with linear increases in compute input?
I think so. So it's important to back off. I think general comment, most academics tend to be, we're held to a very strong norm of assertion, where if we say things and we can't back them up very well, we get mobbed. And so we're very hesitant sometimes to make assertions in an area where we think it's hard. So if I were to claim, I think this is the right model of how intelligence grows in hardware, namely like log linearly, I would get murdered because I don't have the evidence for that. So like the best I can claim is, here's some things I know that like might measure intelligence, like chess elo, go elo, weather prediction, protein folding, and like everything I know of that like kind of could track intelligence goes log linear intelligence. And like maybe you mean something different by intelligence and we can talk about it, but like at least as a preliminary starting point, it's like pretty non-obvious that it does. And then you get into really strong claims if you do want intelligence to go linearly and better in hardware. Like, okay, we get 33 million times, more transistors in a fixed area. Do we really have 33 million times more intelligence? If we do, then I might like want to ask what we mean by intelligence and why we're so worried about it.
Yeah, I would certainly agree. Like if you consider the 33 million, I'm not entirely sure precisely what year that's from. But if we...
It was 55 or 60. I crunched it in the paper. It was something between 50 and 60 years inclusive.
Yeah, it seems really obvious that compared to the Dartmouth conference, we are very far from 33 million times better, right? That's something I think...
Were they working with singular perceptrons back then?
And
sounds right.
saying they were
Yeah.
almost there. They could do it in the summer.
Yeah, that was very wrong.
I think, see, the thing is, if you're looking at a single layer perceptron with like, I don't know, 10 neurons, and you're like, well, current GPT-3, or sorry, GPT-4 is like 33 million times more intelligent than that. Um, and it's like, I guess you can also make an argument about a human brain being 33 million times more intelligent than like 10 neurons working together. It's like, it feels intuitively not obviously false, but also like I get your point that like progress has been very discontinuous and like messy, but like given how low their performance was back then and how unintelligent things were, how utterly unintelligent, like just a literal handful, like the number of neurons I can count on my fingers in a single layer, it's not obviously false to me. What do you think about that, David?
Um, yeah, so I said in the paper I didn't want to push on what we mean by intelligence. Like, obviously it's not my word, but I got kind of frustrated that everybody said, the problem with the singularity hypothesis is we don't know what we mean by intelligence. So I didn't want to push it. I think this is one place where we might need to say what we mean. Namely, there's two claims that are hard to keep in tandem. Claim one being, since Dartmouth, machine intelligence has gone up 33 million times. And claim two, as soon as it gets, one or two orders of magnitude above the human level, we're all dead. Or like even, one or two orders above the human level, the world is completely transformed. Like these claims don't play nicely together because if you think the kind of change we've seen is, 6 or 7 orders of magnitude already, and then you're really worried about 1, 2 orders of magnitude above us, it's like one's trying to make that look small and one's trying to make that look big, and they don't gel.
Yeah, I mean, I feel a bit sorry that I wrote that this is totally an absurd claim that intelligence has increased by 33 million over this period. I think you could argue even more. Like you could argue that some of the first chips that were designed had something like 100 transistors, and you can buy an M1 chip right now that has 100 billion transistors. So are we seeing something like a factor 1 billion? I think that is
Yeah,
really
like
hard to
like in
argue.
general, I still think it's like a false claim that intelligence has increased by a factor of 33 million
Yeah.
because I ran it through my logarithmic model and it says it's wrong, therefore it's wrong. Okay, that's a joke. Anyways,
Yeah, I tend to agree.
Yeah.
Bostrom would
Yeah.
not try to weasel out like this. He would lose almost all of his epistemic credibility in
okay.
philosophy if he were to. Because
Yeah,
the whole point of this box is he's trying to say, how is recalcitrance and optimization power going to go in the future? And he says, I'm going to give you some history to tell you how it went in the past. And he says, constant optimization power gave us, 18-month doubling of intelligence. And so if he backs off from that and he says, I didn't mean that, well, then he has to say, I was just saying a bunch of irrelevant nonsense that had nothing to do with what I was telling you to project forwards. And that would be, Boston wouldn't write in that way.
So,
so
like, imagine that you are doing something else, like increasing some kind of engine, and you're getting the engine's performance doubled every 18 months. And you are saying that this is the kind of argument that this rate of improvement of doubling every 18 months is kind of the same kind of doubling that you see in Moore's law. I think that is a well-formed statement, is that you're arguing that a doubling in 18 months is a thing that happens more than, like obviously, the transistors didn't double in engine characteristic performance.
Yeah.
That
So
doesn't
when you
make
talk
sense.
about an agent's performance, do you mean an agent's intelligence, or do you mean, the thing that happened early in the transit presentation where we changed the view?
So what I when this the way I understand Bostrom here is that someone is building an AI that is gradually becoming more capable, and
No,
the
no, no. He was quite explicit. This was a claim about intelligence. The entire section 4 is structured about intelligence change as factored into optimization power and recalcitrance. And
yes.
this entire chapter is about the rate of intelligence change. He would not equivocate like that. That would be very poor epistemically.
Um, so,
I mean,
yeah,
from a specific chapter from his book.
Yeah, this is
yeah,
chapter 4. So the
yeah,
kinematics of intelligence
yeah.
explosion is chapter 4. I can pull it up if you want.
I think it's
Yeah.
available on the internet. I think I like pulled out the relevant parts here, and I would agree with you that it is in fact quite possible to read this as Bostrom is saying that the intelligence of the systems implied by Moore's law have been increased in intelligence every 18 months, and that is a way to read this. I feel that the reading that increasing doubling per 18 months is the same kind of improvement as Moore's law, but without a unit. So it could also be that like airplanes get faster according to some improvement characteristic. So did that make sense? Like without a
Yeah,
unit?
he's too smart to do this. So like when I told you, when I heard you guys, look, I'm talking about intelligence. As soon as you change this to like a claim about power or capabilities or whatever, we're in a different realm. He knows that. And if he writes, sometimes about intelligence, sometimes about power, sometimes about intelligence, he's going to get the same equivocation worry I raised against Chalmers. And like I disagree with Bostrom, but he's like smart enough and high integrity enough. Very low probability that Bostrom would intentionally equivocate like that. And you can accuse him of accidentally equivocating, but
Mm.
I mean, I have my disagreements with the man. I don't think I would much rather say that he said something false than that he was trying to do something slimy.
I'm not accusing Bostrom of doing anything slimy. I am saying that the text can be parsed in two ways, and I think Bostrom meant interpretation one and not interpretation two. Um, so but I agree. This is written in a way that can be interpreted in several different ways.
Yeah, if he's not talking about intelligence, I would be very upset with him. I would need textual evidence to suggest he was no longer talking about intelligence because he knows better. I would not accuse one of my colleagues of doing that.
I have a question about your um, opinions on intelligence scaling in biology, like how it increases in like neuron count increases intelligence. What's your general opinion on that?
Oh yeah. Okay, I mostly want to defer, and I know this is frustrating. So I take it nobody thinks that intelligence scales in lockstep with neuron count, because otherwise, just like elephants and whales would be the smartest. So if I
Um,
remember right, like a couple decades ago, somebody started saying maybe it increases in like neuron count normalized by brain size or normalized by mass, body mass or something.
Yeah, that was the encephalization quotient.
And so, go ahead.
I think now the standard is something like a mixture of cortical neuron count, uh, the
I think
speed
I
of
think
synaptic transmission, neuron
yeah.
density, and a few other factors. But it's encephalization, I think, is out of favor in
Yeah. So,
current
and that's
models.
exactly why I mostly want to defer is like, I'm not
Um,
um,
yeah, I
the
get
cutting edge of the
yeah, I get what
science.
you're
I would
saying.
prefer literature.
I was under the impression that the animals with bigger brains than us had them either like not in the cortex or had a weird arrangement where like in whales half the brain is active and half the brain is like asleep and it's like some kind of weird thing. And also like is it possible that whales are human level intelligent but they couldn't develop civilization because they didn't have thumbs? I think it's reasonable. I think orcas are really cool. Uh, I wouldn't be surprised if they were like as intelligent as a 12-year-old. That would
That's
not
a
surprise
little
me.
strong. Do you have evidence? Like sometimes
I think
people
that's
are pretty hot on like pigeons and starlings and primates and maybe octopi. I don't know that much about whale cognition, but like, do whales metacognize?
I They definitely like recognize themselves in mirrors like a bottlenose dolphin does that. A bottlenose dolphin like can figure out that that like something novel in its environment is something that the researchers would want it to play with, and it understands that things that researchers wanted to play with, like this should result in it being rewarded. Like it can figure stuff like that out. And that's a bottlenose dolphin, which is much less intelligent than an orca.
Yeah, we can talk about the specific results, and we can talk about like different kinds of cognitive explanations of these results.
And the other thing with just to get this out of the way with the elephant is that like I'm pretty sure their cortical neuron count is actually around humans or actually a bit less. It's just that the vast majority of their brain is their cerebellum, which actually just controls their entire trunk. Like they have extremely dexterous trunks, and most of their brain like handles coordination with that.
A final question on that, and I think we should return a bit closer to the paper. If you have an answer, David, to this.
Okay.
Or...
So it's just generally what do you think? Do you think that the intelligence of an organism, generally speaking, increases with its brain size? And would you agree that like if you had something that was like cognitively somewhat like a human, that roughly the cognitive shape of human, but like had 10 times the neuron count, it would like result in something that it would result in really quick economic growth.
Oh, okay, that wasn't where I thought you were going. I mean, in general, the relationship between neuron count and intelligence, I'm going to want to defer to the scientists. And like my not great understanding is most people think a fancy function of neuron count scaled by like what kinds of neurons and brain structure and body mass and whatever, like intelligence increases in that in some way.
But do you think it's possible for something to be like biologically much smarter than humans?
Possible, of course. Yeah, there's no reason that like humans are the upper limit of intelligence space. That's why I don't pull that kind of thing in this paper. I just said, right out of the paper, I'm not going to do that.
And what do you think the economic consequences of such a biological organism would be?
Sorry, that's way beyond my area.
Let's return a bit to the paper and to the singularity hypothesis. Like I tried my hand at giving some kind of intuitive argument. I like here I feel like I am maybe putting some words in your mouth by saying this doesn't really look parsimonious. So I hope you didn't mind that too much. And then I tried here to like give my intuition over the next slides for why this kind of thing is actually a simple model that is easy, that is natural in some sense, in the same sense that linear and exponentials are natural. What were your thoughts when you saw my argument?
Yeah. I think sometimes people get a little bit obsessed with simplicity and Occam's razor. If you talk to, philosophers of science about confirmation, people do tend to think that simplicity is an important virtue of theories. So, sometimes people will say your prior should be weighted towards simpler things. We don't tend to think that simplicity can take you that far. So, my first life in philosophy, I was a logician. I wanted to work in set theory. And famously, the most simple hypothesis in set theory is V equals L. The only sets there are the constructible sets. And it makes everything really simple, and it gives you answers to continuum hypothesis, everything else. But, everybody thinks all those answers are wrong. It just takes every open hypothesis and makes it wrong. And so, people said, okay, it's simple, but that just didn't get us that far.
I'm a statistician, so my impression is that if you apply a logarithmic fit to anything, it'll mostly work. So simplicity does, in fact, work.
Sorry, if you apply a logarithmic fit to anything, it works?
It's a joke.
Oh, yeah, sorry, I didn't sorry. I couldn't see facially, but yeah, we can talk about simplicity I'm mostly just not that enthusiastic about simplicity, and I find, and I think a lot of philosophers find
Yeah.
simplicity a bit harder to assess. Like, I didn't really say hyperbolas are less simple than, linear or flat or exponential functions. I think they probably are, but that wasn't, when I said it was surprising, I didn't say it wasn't simple. It's like, think about all the patterns found in nature. There are very few hyperbolas, and the ones we have don't last long. So, population fizzled out after one order of magnitude, was arguably hyperbolic for a little bit. Nuclear chain reactions, and then they're over in a flash. And so, like, it's not that this is surprising in terms of, like, its mathematical form is complex. It's surprising is because this is a model that nobody ever writes down for anything. And so, you send this to an empirical journal, and they're like, I've never seen a model like this. If you don't, kill them really quick, like vaudeville, they're just going to kill you and desk reject the paper.
Yeah, I think that's in general. I would agree with you that this kind of reasoning on priors isn't that helpful. What are this here? I have a claim here. I think this is a bit close to one you're making. That we have improvement in transistors per chips, and that was a kind of improvement that didn't cause an intelligence explosion. And then my answer is that this isn't an example of a recursive improvement process, and only becomes a recursive improvement process when it compounds in the same way as interest compounds.
I'm sorry. I actually disagree with you there, Soren, because
maybe we can just have David answer first.
Oh,
and
yeah,
then
sorry.
comment afterwards.
So the argument on the left, we've had improvements in transistors per chip, but it didn't cause an intelligence explosion, is not the argument, right? So this is a section arguing that we should expect diminishing research productivity in growth of AI per weight, whatever weighted research input. And I said, look, one natural kind of way to measure AI growth is hardware. If you have the bitter lesson in mind, that's like what we're growing. And like that thing not only has historically showed diminishing returns, but like it's the star case for diminishing returns in one of the best papers. So like the claim here is just, we have pretty good reason to think there's diminishing research productivity here.
Okay.
I think Carl Schulman's made the argument that there is diminishing research productivity, but it's not so rapidly diminishing that if you were able to double the number of researchers, if you double the number of chip production, that wouldn't counteract diminishing returns. Like I think he's made some specific claims about the shape of the, I guess you call them production curves, saying something like chip production, like, I don't know, it requires not that much more. Like if you increase the amount of labor going into chip production, then you could still see very rapid growth if you can scale the amount of labor with the amount of chips. And I guess the thing I'm trying to get at here is that it's unclear to me if the diminishing returns are so diminishing that you don't expect to see a big blow up, say within a decade or two.
Yeah, that's where we want to be with all these arguments. It's like, look, the claim of the paper is a hyperbola is a strong claim. It needs strong evidence. And actually, you need a lot more than hyperbola because, like, maybe you need a hyperbola in intelligence, which is harder than a hyperbola in hardware. Or, maybe you need a hyperbola despite diminishing research probably dragging it down. And it's not that you can't, write the equation for a hyperbola anymore. It's just you need progressively stronger and stronger and stronger assumptions. And if you're already starting with a pattern almost never found in nature, and then it's getting harder and harder, you're losing people. So there's argument you made. I don't read Schulman, but I think you're probably running that kind of argument that people run with macroeconomic growth models, that if you get perfect substitutability between labor and technology or capital, that you get, a hyperbola in economic output. Was that the argument?
It's something of that flavor. I think the specific claim is about increasing the quality of hardware and how this would, like, how that depends on labor into chip
Yeah. I guess
and how that would, what would occur if you were able to route all of your chips into higher quality labor, which routes back into chip production. With a
methodologically,
specific
I would
claim being, oh, go ahead.
strongly urge doing one of the following things. Either one, deferring to economists, or two, publishing papers in serious econ journals arguing with economists. So this kind of economic singularity-based argument, which you can translate into a technological singularity with some assumptions I'm not going to believe, but whatever, that, you just take standard macroeconomic growth models, you plug in labor and technology being perfect substitutes, and then you get an intelligence explosion because, more technology means more labor, and that's great. This is something that's in the economic literature. I cite the Nordhaus paper on it. I cite, the Aeon paper. It's like serious economists are now willing to talk about it. Almost all of them think this is nuts. And so, I wrote an EA forum summing the Singularity Hypothesis, and Jaime Sevilla, I think that's his name. He's, if I remember right, he's got some graduate training in economics, whatever. He said, what do you think about this economic argument? And I said, I'd recommend you either defer to economists or, hire serious economists and try to convince them. And he said, somebody commented, I don't think it was him, somebody commented below, no, we've given up on economists. We know they're not going to believe us. And it's like, as soon as somebody says that to me, I'm like, okay, every expert in the field thinks this is nuts. They're not trying to convince the experts. I'm not an expert in this field. What am I meant to believe?
Yeah, I would agree that this is a cop out, definitely. The correct if you make an economic model and you can't explain it to economists, then I think that is a very strong evidence that your method has a substantial problem.
But this is like this kind of lack of engagement with peer review. So we're pushing things that are outside the mainstream is really common. So the Tom Davidson model, OpenPhil publishes this Tom Davidson paper, and then they asked some people to review it. I don't even know who else they asked to review it, but they asked me to review it, and I said, one, I'm not an economist, get an economist, but two, my opinion is this is unpublishable. This doesn't meet minimal scholarly standards. The main argument is a bunch of bullet points in the appendix. And, the guy's smart. It's got, things going for it. But, the way this is constructed is just not up to scholarly standards. And then they just go ahead and publish it anyways because, they can put it on their website. But then, I'm looking at, American Economic Review that's gone through, the murder factory. Economists are really mean to each other. And, leading economists in the world said this is good. And then I've also got, a foundation that, well, lo and behold, publishes another paper saying that they're right with going through, no meaningful peer review. And, who am I going to believe?
Yeah, I think this is an interesting and very reasonable a reasonable point, but there's also this anthropic argument that says that obviously something that will kill us is by definition something we haven't seen before, by definition. So if you're postulating something that
I mean, if you're starting with unpublishable economic models, and then you start going into anthropics, I think that's a very bad sign.
But this is what, I've been begging people to write peer-reviewed papers. So literally, everybody asks me, David, why are you writing about Singularity Hypothesis? Because nobody cares about that. You should just write about instrumental convergence. And I told my boss, I'm writing about the singularity because two serious scholars, Chalmers and Bostrom, took the time to write it down. And, at the time I was writing this, there were no serious papers on the instrumental convergence argument, and there still aren't many. And so, I need peer-reviewed literature and good journals to engage with. And this strategy of, posting a bunch of things on forums and then complaining that it's being ignored, I mean, we ignore things on forums all the time. That's how research works.
Yeah, in general I agree. This is a very sad state of affairs. The quality in discourse around AI safety compared to many other much more healthy epistemically fields and much more academic. This is unfortunately a sad reality. I would agree.
I
I
am not sure I agree. I think that the state of epistemic discourse is very weak, but I don't think it's true that it's much weaker than. I feel like a lot of academic fields are also very unhealthy,
That may be.
especially areas where you have poor feedback loops, where you have noisy signals, where you have where experiments are very costly to run, etc. And I think that like if I compare alignment to something like I don't know high energy physics, I don't think high energy physics is actually epistemically more helpful. Well, high energy physics or or a lot of philosophy or some parts of macro econ, whatever. I don't think it's actually much more or less epistemically helpful. So I'm not sure peer review would actually help because I feel like part of the issue here is that a lot of these things are talking about models taken outside of the context they were built in and applied to situations they were not like the people who invented them, the challenges that they were driven by, invented for, didn't intend.
I'm
And
gonna be
like,
honest. I'm sorry if this
yeah,
is too mean. So, like, effective altruists started with the highest epistemic standards anybody'd ever seen. It was great. They said, we'll only accept randomized controlled trials, you know, to macroecon. They were really raising the bar on charity, and everybody loved them. Standards have taken a nosedive to the point where regularly you will hear long-termists say exactly what you said. I don't know that there's any value to doing a PhD or publishing in serious journals or following, you know, expert consensus or even talking to economists because clearly you don't talk to them. This is completely insane. And when you say things,
that's not my claim.
yeah, well, then what is the claim? Because you just said that you don't think there's any more epistemic value to theoretical physics, which is one of the most rigorous, difficult,
High energy
intelligent
theoretical.
fields. Like you can't be knocking the smartest and best developed fields in the
Can,
world with the best
and
epistemic
will.
system
I think
saying
high energy
internet
theoretical
forums are a replacement. It's
highly
just not a
successful.
replacement.
Right? Like if I compared it to condensed matter physics, condensed matter theory, I would say obviously that's way healthier than alignment. Like it is a joke to compare the two. But high energy theoretical physics, I feel much more comfortable saying that's very epistemically unhealthy. Like people are just kind of floundering there for the past 4 decades.
I think it's kind of like seeing how the sausage is made in your specific field can make you very cynical towards it. Like I work in cancer genetics, and I am extraordinarily cynical of the state of the field. And if and when a a relatively high quality journal publishes a relatively highly received paper, my initial reaction is that it's probably not true. That the conclusions probably aren't true.
I
Well,
think
okay, that's not entirely true, but like I'm very suspicious on it. I'm very suspicious about it.
I'm gonna be honest, you people are
I,
scaring the heck out of me, and I do not think you know how many leading researchers you lose when you say things like this. Launching attacks at established research infrastructure, established journals, established universities, established hierarchies, established bodies of knowledge it's anti-intellectual, it's bordering on conspiratorial. And when you're using what most people are going to regard as very low epistemic standards and getting to conclusions like AI is going to destroy us all, this is where people just stop listening. That this is not something that is going to get you any traction in research circles.
I think I would agree, and I'm just gonna interrupt Ali and Larmain to perhaps we could focus on this part that I have on the screen here, on the arguments from bottlenecks and physical constraints. So there are in fact obviously physical constraints, but it seems they are very far from what we have, and so this seems to be things that are very unlikely to constrain hyperbolic growth at least until it gets dramatically above the human level. Do you have any particular physical laws or physical constraints that you feel are likely to be binding?
Yeah, sometimes I wish I'd combined the, bottlenecks point and the physical laws point. Like, they're conceptually distinct points because I wanted to split them, but in general, I'm more enthusiastic about the bottlenecks. These constraints take a while to overcome than the laws they don't ever overcome. So, if you want a trillion times more hardware capacity, you need a trillion times more hardware manufacturing, and that's really hard. Or you need a trillion times more energy, and, oh my God, we're all panicking about how we need cold fusion now. Those, I think, I want to lean on much more than like we could never get enough energy or we could never get enough raw materials. If we did want to talk about physical constraints, I think a couple that are scaring people, heat dissipation, transistor size, and quantum uncertainty. So, transistor size and quantum uncertainty is just we've got transistors that are, what are they, like 10 times the atomic radius of kind of a average atom-ish. And like, that's small and that's fine, we can do it. But, you start going orders of magnitude beneath that and you're in like a completely different ball game of how physics works and the kind of things you need to worry about where, things like quantum uncertainty were really, who even cares? You get small enough and you care. Or things like, it's smaller than an atom or like hard.
Yeah.
And then energy. I mean, I think a lot of people think the reason Moore's law is in trouble is, you make it twice as dense, twice as dense, twice as dense. You got to dissipate twice as much heat, twice as much heat, twice as much heat. And that a lot of people are thinking we're losing the capacity to do that. Maybe that is a bottleneck point. I think if I could rewrite this, I would have put more emphasis on bottlenecks and less emphasis on like the never. Because it makes me sound like the crazy person who's like, there's a fundamental limit in intelligence space and we're close to it. And I don't want to go for that.
Okay, so just so I understand, like obviously Moore's law, it says the number of transistors on a chip, but just what we really care about is like how many transistors are packed really close, but more like how many transistors in total. So you could get around all this by all these problems that you're mentioning by just making the chips larger, right? If you make the chips 100 times larger, or like build more chips or something like that, then you could just very easily get around the heat dissipation problem.
But certainly, semiconductor people are talking about how to get around all these problems physically. And I know there are solutions proposed.
I'm actually
I'm
curious on
willing to
what.
defer a little. I'm a little bit skeptical that it's that easy, but I am willing to defer a little.
So when you say physical constraints, are you referring to like how qualitatively intelligent a specific, well, qualitatively, we're using the term quantitatively, I guess, but which is what I actually mean. That are you referring to a specific upper limit to the quantitatively intelligent a single agent is, or the overall?
No, I just meant, things like if you have a bunch of transistors, you generate a bunch of heat and you got to get rid of it. Or like if you have things that are really small, they start interacting in ways that, kind of wash out with things that are really big. Yeah, I didn't mean to
Yeah.
be like there's a fundamental constraint in intelligence space. I'm really trying not to make that kind of an argument
Okay.
here.
Yeah.
I. Sorry. Go ahead, Soren.
Yeah. So like my argument for the standard way to get around this issue that you can't have as many transistors as you want on a chip is to put them in a data center instead, because a data center you could you can have a huge number of transistors in a data center and you can get around the energy and heat dissipation and quantum effects there easily.
Yeah. Maybe focus a little more on bottlenecks. So like, if you want to say, I think at one point the claim gets made, we're going to talk about a 24-hour doubling time at some point in the singularity. And, if we're going to go with a bitter lesson that 24-hour doubling time means 24-hour doubling time of chips, like we're imagining, a super efficient robot manufacturing chip doubling the plant, doubling the supply of chips in 24 hours. And that's, a type of manufacturing that I think stretches how most people think about making chips today.
I would agree.
It's interesting
This is
you would
for
say
policy.
that. It's interesting you say that specifically, because I can imagine like what right now I think the failure rate for like chip manufacturing is pretty high. It might be above 50% for some things. So like just for your very narrow example, I guess maybe you can like have a really good quality control software that reduces the error rate considerably. So now basically every single chip printed can work. But like I still definitely get your
Yeah.
argument.
I mean, I guess, look, right now, NVIDIA is like everybody wants to work in NVIDIA. They're going to like a $3 trillion valuation. Like right now, anybody who could quickly and cheaply set up a chip manufacturing plant would like love to. And so, it's not like there's not that much demand. It's just like the idea that we could, get double as many chips in 24 hours. It's like right now, no.
Yeah.
And like
I
maybe
definitely agree with
a
you.
one-off doubling, but if we have like double, like a bunch of doublings really fast within a year, the world has 500 times or 500,000 times more chips. That's a very different manufacturing regime than NVIDIA stock price going through the roof because it takes years to build a plant.
Okay.
I would
Um,
agree that this kind of like sub 24 hours doubling time is something that I exclusively think of, or almost exclusively, through like this that intelligence is something that, in a qualitative sense, can be like written down as a simple computer program that can then be improved or something like that. Not through hardware. I think that building twice as much
Yeah.
hardware over 24 hours seems very difficult. Whereas if you get a really good Gears level understanding of intelligence, which we really don't have right now, if you do get that, then there are a number of times where people have figured out really smart algorithms that have dramatically improved performance very quickly.
Another thing is that like you could have the classic online superintelligence that just like hacks a bunch of computers around the world and is able to, get like 100x or 1000x as much compute in a very short period of time that way.
That was
Well,
a classic.
yeah.
Do you want to answer?
That's not really possible like a year or two from now, because in a year or two from now, like the vast majority of AI useful compute will be in AI training data centers.
Yeah, I think it's when Bostrom made that kind of prediction, it seemed like a thing that could happen, but I would agree that this is probably not a thing that's going to happen.
Yeah, this is sitting uncomfortably with deep learning. When we write down scaling laws, so there's like two paradigms. There's, the scaling law paradigm in terms of, smooth curves when you increase things like, number of model parameters or compute or whatever, that, you get a smooth increase. And then there's the, emergent abilities. It says, never mind scaling laws. Sometimes we just get a qualitative jump. And I had a referee ask me, like, okay, you talked about kind of the scaling law model, but not the, emergent abilities. What the heck? I was like, okay, number one, like if we talk about scaling laws, nobody's writing down hyperbolic scaling laws, so like that would be weird. But like number two, when we start writing down these emergent abilities, the kind of core argument for the singularity about recursive self-improvement has gone out the window. When we talk about this like one-off jump, we've taken away the most powerful argument for the singularity was supposed to be recursive improvement, and we've just recursive improvement was supposed to be good because you only have to get 2 times better and 2 times better and 2 times better. And now the argument is we're going to get 10 million times better overnight, and that's actually like a really hard sell.
Is it though? Like, because we do a lot of like software research, like people publish papers and look at which algorithms can make deep learning more efficient. So I don't think it is unlikely. I mean, we already do see small examples, like really inefficient examples, like NVIDIA's like slightly better matrix multiplication algorithm stuff, which I don't think is very useful. I don't think it's actually, is it even implemented into their chips? I don't think so. So it's like, do you think stuff like that is possible?
But that's exactly the point, right? When we talk about software improvements, we can talk about getting a little better at matrix multiplication. We can talk about big improvements like transformers, and these are impressive. We get jumps. I don't think anybody thinks the intelligence of a system has jumped 1 million times or 10 million times through one of these improvements. I tend to think people
Oh, right. Yeah. So
Human would expect to be much more moderate jump.
I think that's a really interesting thing that I've been meaning to discuss since the beginning about the specific claims about multiple orders of magnitude increase in intelligence. Um, about that being a core claim of a lot of the singularity stuff. I think we would get to a something that Ray Kurzweil I think would describe as a technological singularity within a single order of magnitude increase of intelligence from humans.
So
I would need textual evidence for that. I think most, and I can give you some citations if you want, most people defending the singularity have been very clear they meant orders of magnitude. So, Dave Chalmers said we were going to go until we're at least as far beyond the average human is beyond a mouse. Ostrom said a worm. Loosemore and Gertzel said 2 or 3
Wait,
orders of
how much more
magnitude.
intelligent
Hausen said
do you think?
orders.
How much more intelligent do you think a human is from a mouse?
Oh, you don't
Because
think
10
that's
times,
2 or 3 orders of magnitude? Because, I didn't want to push on what we mean by intelligence, but if that's not 2 or 3 orders of magnitude, I know how to translate with what you're saying. But now I'm, much more skeptical about getting 1 order of magnitude above humans.
yeah, because how much bigger is a human's brain from a mouse? It's I think 100 times the neurons or something. That sounds reasonable to me. So 10 times the intelligence also sounds reasonably in that context.
I think that
But yeah,
my intuition about intelligence reasonably closely tracks IQ. I think IQ has a large number of problems, but I think unfortunately I get even more confused. I can I've talked with a number of people, probably some people who are in the lower 10% of intelligence and some people who are in the top 10% of intelligence, and that's the difference in things they can do are probably things that I can relate to much more than comparing uh, um, comparing with a mouse. Bostrom has this a village idiot to Einstein as one step, and then imagining a step further. How do you feel about that? Is that roughly an order of magnitude?
Yeah, it's hard because the whole thing with measuring scales is you can, raise them to an exponent or a log or whatever, and you can do this in, utilities with economics. It's rescaling, there's kind of no arguing about it. I'm happy to talk about IQ. Definitely, I think an order of magnitude in IQ, going from 100 to 1,000 IQ is a pretty impressive jump, and going from 1,000 to 10,000. And so, if my opponents are saying we're going to get 10,000 IQ computers, I'm happy to pin that on them, but I don't think it's going to go very well for them.
I just don't want to use IQ because it's statistically it's based off a statistical distribution in humans, and it gets really weird once you go
to
above
agree.
really even 160, even 140 or 130, things get really weird, especially human stuff. But it's I'm still trying to understand your model here because it's okay, so let's say my dog has um what 10% my number of neurons if you assume a logarithmic or something scaling system. I think you can say that at the very least my dog is 10% as intelligent as I am, because if you're assuming diminishing returns with more neurons, do you get my argument? That my dog is at least 10% as intelligent as I am. It can't be less intelligent than 10% because of diminishing returns. What do you think about that argument?
So, when I was asked earlier about how neuron count across species correlates with intelligence, I said I mostly want to defer. And there's probably some correlation, but it's probably pretty complicated. And we should probably ask the scientists. And so I mostly want to say that. But I don't think we want to just straight count neurons.
Yeah,
I'm,
I would also like to table that discussion. Um,
it's just I'm just bringing this up specifically because we seem to be operating on completely different scales. And my model of your scale is that there is diminishing returns. Like I definitely think that you think there's diminishing returns in like for neuron counts, for like computational inputs in machine learning. So it's like the difference between, so yeah,
Uh,
what is my
Diminishing
idea?
return phenomena are scale independent. If you have diminishing returns on one scale and you rescale, you still have diminishing returns. It's just, the rate of you can't like have diminishing returns on one scale and increasing returns on another, or one of them's a bad scale.
Okay.
so
What I'm trying to say is that you can't, let's say that it takes 10 times as much compute to train GPT-4 than to train GPT-3. My claim is that in your model, you um, because your model presupposes diminishing returns, you can't say that GPT-4 is more than 10 times as intelligent as GPT-3.
Probably, yeah. So again, in the paper, when I talk about diminishing returns, I'm talking about diminishing research productivity. So, the relationship with routine research inputs and research outputs. And I'm not entirely sure that's a great way to think of like adding neurons as research inputs. I think I'd be stretching it a little bit. I think most people
I
probably
don't mean
do think
neurons. I don't mean
like,
neurons when I'm talking about machine learning. I mean computational inputs like compute and data.
yeah. I mean, I think almost everybody is going to think 10 times as much hardware or compute or, whatever is going to get you not 10 times as good a system, but a little less. But I wouldn't. Certainly, I think a lot of people are going to argue that.
So I make a very specific claim here that on this slide that it depends on like how fast are the exponentials in some sense. That if you are making a recursive self improvement that has a factor a, and then you add a complicating factor that you can't get that you only get a exponentially bad return on getting more processing speed, for instance. And then it depends on these two. Do you think this argument carries that sometimes this kind of diminishing returns blocks a singularity, and sometimes it fails to block a singularity?
One thing I would like a lot more of from the Singularity folks is empirical evidence and empirical argument. That I often see someone like Solomonoff just kind of write down a model and be like, yeah, this is the model, this is hyperbola. And it's like, okay, we all know how to write down the equation of a hyperbola. The question is, tell me why this is a good model. And so when we talk about rates of diminution, for example, I'm giving you American Economic Review, and I'm like, look, this is what we know about why research processes tend to show diminishing returns and kind of the rates that we tend to show returns for. But I don't really know how to respond to someone just showing me the equation for a hyperbola. Like, that is the equation for a hyperbola, but I need data.
Yeah. Okay, so that's a fair request. So one person who has definitely made this is Kurzweil, who tried to graph a large number of yeah, I can't precisely remember. He had some strange criteria for which things
Yeah.
he wanted to include. He also included the things that I care about, which are the recursive improvement things for humans.
I
Like
mean,
we,
look, Ray Kurzweil thinks there's a law of accelerating returns. The law of accelerating returns is almost every growth process in the universe shows accelerating returns. This is completely nuts and nobody takes it seriously, right? I mean, almost any economist is going to tell you diminishing returns are the standard regime. So the whole, Kurzweil, I'm going to show you that across anything you would care to measure in the universe, we have accelerating returns. It's just like, this is raving lunacy. This will never be published in a serious journal. We can talk about these, like when you start talking about like historical milestones and they've gotten like twice as fast, twice as fast, twice as fast, twice as fast, we get kind of the issue we talked about in general where like we can't literally mean that because, eventually we get, every year a milestone and then every day and then every second and then a millisecond. And like, so everybody thinks we need to, lodge it out at some point. and we can argue about that. But I tend to think a lot of these arguments that, the data and what goes into them is finessed in a way that is gonna not survive review at a good empirical journal.
There's, like, I think obviously I would agree with you that Kurzweil is making a number of bad assumptions, but I also feel that this kind of, like, if you try to look at the things that are recursive in some ways, the ways that we improve, such as like education and writing and culture and being able to speak, the internet, all these kind of things seem like they very strongly point in this. Of course, it won't, like, Kurzweil makes a number of bad claims, including, of course, we will need at some point this kind of singularity will stop. But like the empirical idea that if you look at the things that could be said to be recursive improvement and try to graph them over time, you get a strong singularity, right?
I don't. Could you give me some examples? I don't know any examples of like serious recursive processes in nature that we write hyperbolic models. Is the idea that like if I graph educational attainment over time, it's a hyperbola?
No. No. Like if we graph the difference in time between, we get some kind of recursive self-improvement to humanity, we will see that this, in fact, follows it's a straight line on double logarithmic paper, that this is following this precise model. Like if you
But
take
improvement in what? Like improvement in educational attainment or in like healthcare patents or like agricultural productivity? Like what's the thing that's improving hyperbolically?
yeah, the thing that is improving through this is our general capacity. Unfortunately, I don't have a the
I
precise.
think
I'm pretty skeptical.
I think I'm getting Soren's argument. Like, it's like, okay, if you're looking at from the point of the 1970s, human population is growing exponentially, and also the average human is getting more intelligent, and also like we are getting better research tools and better computers. And once you have all of these factors add together, we will get to something unrecognizable before like human population stops going exponential. I think that's a really bad argument because it's obviously false.
Yeah. That's not a great idea. So like population growth is supposed to stop and then start to reverse by 2100, and we're supposed to be within 50% of the cap. So, population growth in the near term is not supposed to take us to a meaningfully new regime. Um, when we talk about growth of intelligence, there are things like a Flynn effect. Those tend to be much slower than exponential. Like it'd be really cool if we were getting much more intelligent really fast, but like our brains don't change that fast.
Okay, David. So I've been thinking about that weird argument I had with you earlier about Einstein. I think the main thing that I disagree with was just having a model with diminishing returns and also having like with diminishing returns in like terms of neuron count, which seems fuzzily like your model, and also having Einstein being 10 times as intelligent as the average human, because then it's like,
Oh, yeah, that's pretty strong.
so do you see my point?
I didn't mean to claim that Einstein is 10 times as intelligent as the average human. Was that a claim that was made
I think
somewhere?
I think you mentioned that offhand. I think I was like, Soren asked you how much more intelligent Einstein was than the average human, and you said,
Oh.
yeah, maybe an order of magnitude.
Oh, if I said that, I did not mean to. That's a very strong claim.
How much more intelligent do you think Einstein was? So, I'm not asking for rigor, just like I'm trying to figure out your model here.
Or like, because none of this is my model. It's all me trying to figure out my opponent's model. And
It's
it's kind of
just
hard because
specifically.
like you can rescale. I mean, my natural model would be something like IQ modulo IQ being a little racist, but like, much less than twice as intelligent. But there's this thing that you can't really argue about scales because you can always rescale them. And like, if all you care about is the ordinal ranking, you can just change change the difference arbitrarily. Like you preserve ratios
It
maybe, but like the
it's
cardinal,
just it's just specific stuff about you click on your scale. You do have an implicit scale where you say, okay, these people,
oh,
they're saying that intelligence will need to increase by several orders of magnitude.
oh, no, I
And you
don't.
mentioned, and you also mentioned millions of times as intelligent at one point. Like it's weird stuff like that.
Yeah, but I was picking on
Yeah.
that, right? I was saying, so if you think that intelligence grows linearly in hardware, then you should think we've gotten a 33 million times increase in AI. And I said, if you think that, but you also are scared of one or two more orders of magnitude, that's hard to reconcile.
Oh, okay, yeah.
But I was picking on
But
that.
okay,
Hmm.
but what do you think actually happens if we see an order of magnitude increase?
So, I mean, I argue in the paper that intelligence grows probably sublinearly in
Okay.
hardware, with the caveat that, again, I'm not qualified to make that claim, so I back off. And I'm like, as far as I know, most reasonable things we would call intelligence have tended to grow sublinearly in hardware.
Okay.
Um,
Um, but people are investing huge amounts in these systems, and like there is a sense in which they're close to human level, like because you
that's
can
right, that's
talk to,
right.
because you can
So
talk
that's
to
how we
them.
got Moore's Law, right? We had diminishing research
Yeah,
productivity, but we just ramped up the investment. So, how
yeah,
did we keep Moore's Law going? We spend more and more and more money. And now it's like
yeah.
$10 billion to build a manufacturing plant, and then give me $7 trillion and I'll build AGI. And, the money's going up and up and up and up. And this is a game that can't continue because the money's getting really big.
And I'm saying that because we're close to human intelligence now, like another order of magnitude increase in intelligence would mean something like that blows past humanity.
Yeah, so people who think that are going to be much more bullish on, blowing past humanity soon.
Mhm. But do you think like the physical limitations or the economic limitations prevent that?
So, like, the Dartmouth people and a lot of the early AI people were really bullish, and it didn't look good. They all said we're 5 years away, 10 years away, a summer away, and they were wrong. And so for the longest time, the rule in academia was you didn't say how close you were to AGI because you were just going to look good. And I think us, the people who are most bullish have started again making predictions. And it's really hard because the people who aren't bullish are the ones who think that this making predictions is kind of a mug's game. And like, it's a fair question, how far do I think we're off? I'm hesitant to predict. And then you say, okay, David, aren't you afraid to be wrong? And like, of course I'm afraid to be wrong. I think I can't do it. That's why I won't do it. And I realize that's frustrating. Like, it's really tempting to, go to the only people who will give you numbers, who are the like bullish people. But like, most people are not willing to give you numbers because they don't think we have a good basis for these numbers.
I
Okay.
did, in fact, give a number here. So maybe I'm the kind of people that I said my P singularity is 5%, mostly based on the fact that it seems that we are not really trying to improve intelligence in a qualitative sense. We're just, stacking more layers and trying to build bigger large language models, and we're not really trying to like understand intelligence in a way that would allow us to like improve it. How do you feel about this kind of argument?
Um, I mean, it's lower than I thought you were going to be, which is nice. I don't
Uh,
tend to be as enthusiastic about naming numbers, so like I wouldn't give you a number, but I'm glad to hear that's on the lower side than I thought it was going to be. Sorry, just to warn you, I need to, about 5 or 10 more minutes. I should
Sure.
go. I'm in an
yeah. Sorry
Airbnb and the
about
walls.
holding you up for so
No, no, no.
long.
I would actually stay longer. It's just the walls are kind of thin, and I don't want my neighbors to hate me.
Fair
Okay.
enough.
What time is it?
It's 9:43. I'm in London, so I've got time. But
Oh,
10's a hard
right,
cutoff,
right,
or
right. Okay.
that's bad
Sure.
behavior.
Uh,
Wow. I guess I'm a really bad neighbor.
Well, you're fine. I mean, maybe you have thicker walls.
in the middle of the night also. So this was actually one of the things that I said I didn't want to talk about, but I thought maybe you had some comments on like here, like the Bostrom-Yudkowsky argument where I'm making the statement that this depends mostly on that alignment and AI control is really difficult and very hard, and that how fast we get a takeoff doesn't matter very much if we can't use the time productively. Do you think this is a fair reading of
No.
Bostrom's argument?
So, like, the first thing you said, that orthogonality is kind of minor, is totally right. Like, the only reason we put orthogonality there is some philosophers want to deny orthogonality, and I don't. No, the Bostrom-Yudkowsky argument is quite explicit in relying on the explosion, and it's explicit in two ways. The first is that it gets us not just like something a little bit more intelligent than us, but much more intelligent. So, the structure of Bostrom's argument is we're going to get something so super intelligent that only motivations matter. If I only give you premises about what it would want to do, like instrumental convergence or orthogonality, that'll tell you what's going to happen, because its power doesn't even matter. It's just this godlike super intelligence. And you can't argue in that way if you don't have, very, very, very fast growth. You need to also argue about what a machine's capabilities are going to do, and he doesn't do that.
I think I have a problem with that, because like there are so many different, like we don't need a sustained intelligence explosion, and it's like, in my point of view, in my model, like I'll repeat that in my model, a single order of magnitude in terms of increase in intelligence is enough to get that there. I think we can get there with like physically and economically plausible investments.
Yeah, that's fine, but that's a different argument, right? That's like Carl Smith. That's not Bostrom. Bostrom doesn't make that argument.
Oh, okay, my bad.
An order of magnitude would be enough to kill us, and Bostrom never writes a chapter said an order of magnitude would be enough to kill us. He doesn't even try for that.
No,
And
he's
like that
trying
doesn't
about-
mean he
okay.
doesn't believe it, but like that wasn't the argument he made.
Yeah. So the argument is more about the speed. Like if we imagine that there is a slow takeoff, then that is also a thing that kills us.
Yes. So Bostrom says explicitly, chapter 4, chapter 5, that he thinks slow trade-off is much more safely friendly than fast trade-off. And so the reason in chapter 4 he argues for what he calls fast and moderate takeoff, and I would say is very fast and very, very fast takeoff. He argues for that precisely because he argues that we would be at much less risk in a slower takeoff scenario. And again, you can deny that, but that's the argument he made.
I think he would. Part of the argument is that, like, the way I understand the argument is that we are in really, really big problems, and the intelligence explosion, if that happens, that makes it even worse. But it is already a really, really bad situation if we have a takeoff that takes a couple of decades, because we don't know how to align and
So
control.
let me read you what he wrote, because he was very explicit here. It's going to take me a minute.
That's very interesting.
Yeah, I would be shocked if he had said something that's consistent with several decade takeoff is very dangerous.
He said almost the opposite of that.
That is very interesting.
Yes, I'm saying that I would be shocked if he had said that.
I don't think.
So, okay. It's going to take a minute. I sent this to a referee, but it was a 47-page referee report.
Yeah, we don't have to actually go through that now.
Okay.
I will also put that on my to-do list to actually look this up.
Yeah, but if you
precisely.
email me, I can get you.
See. I will write that down. Great. I wouldn't mind continuing the discussion.
Sorry,
but-
it's page 64, 65 in Bostrom.
Sorry.
Page 64, 65, and then he says it again. So, also page 78.
I'll have a look at that. Thank you.
Yeah. So here's page 104 is I think the best. The speed of the takeoff may make a big difference to what the outcome will be. With faster medium takeoff, it's likely that one project will get a decisive strategic advantage. We've now suggested a superintelligence with a decisive strategic advantage would have immense powers that could determine the disposition of humanity's cosmic endowment. So that's why, the chapter on decisive strategic advantage comes after the kinematics, is because the kinematics is supposed to make it very plausible the advantage just comes, before we can do anything. And again, maybe he shouldn't have said that, but that's what he said.
Yeah, I will review that. And yeah, thank you.
Thanks.
Yeah. So, do you want to continue, or would you like to?
We should probably, I'm definitely happy to email and talk more, but I should probably let my neighbors go to sleep.
Okay.
Fair enough. So, thank you for joining us, David. It's been a pleasure.
All right.
Thank you for having me. I appreciate you reading my work, and yeah, be in touch.
Great, we will. Thank you. Bye.
Okay. I definitely agree with him that the epistemic state is kind of trash. That's now that I think about it, it's actually kind of horrifying, and also
It's
the
also,
Yakowskian Miri argument looks really, really, really bad from the outside because it relies on anthropics and doesn't make predictions before we die, and
Wait,
also
hang on. Where does it rely on anthropics?
I've read I think it was one of the Litecoin infrastructure people, Harkaryu, the guy who runs the whole thing.
Okay.
He said that he doesn't expect to see signs of empirical evidence of imminent AI doom because of anthropics. I saw that forever ago. Well, a couple months ago, and it really stuck with
I
me.
am somewhat skeptical if he is saying, if you're claiming he is saying that
I
or
that is not what he said. It was my recollection of roughly the